It's 6 o'clock. So I'll just get started. I think we're missing a few, but hopefully we'll get everyone in a couple of minutes. So I'll just take it a little bit slowly at the beginning. But welcome back to our 3 CAD and design class. This is our third class for the course, and this is Jack. We'll begin with reviewing kind of the homework from last week. So the homework was building like the robot arm, which was the stuff between the base and the hand. And I just want to take a minute to see if people were able to tackle it or had any troubles, any concerns before we move on. I know we didn't have much time to work on it in class, so definitely if people had trouble, I'd be happy to take some time right now.
So I created one, but it can't move left and right. Like, am I supposed to like do revolute on them?
So do you want to share your arm for me?
Well, I just did fastens, mate. So.
Oh, I see. Yeah. So
I can just change it to revolute. No,
yeah. Yeah, that sounds about right. So the example arm, this one, all of these are revolute mates for the most part. There's a couple of fastens, but those are to join those pieces together. But these are all revolute because the revolute is what allows it to like rotate like that. In the real world, how it'd work is you might have some sort of like axle, like a rod that goes through the holes, and it's turned by this servo right here. And that rod is connected to like this piece, which allows it to turn. Right. So since I don't have any questions, I'll just move on to the content, but at the end of the slides, we'll have more time to go back to CAD. And if anyone has any questions then, I'd also be happy to answer. But like usual, I'm gonna go over a little bit of like quote unquote lecture material to kind of improve our knowledge, and then we can try some stuff out in CAD. So this week, we're kind of talking about a topic that we touched on in CAD Level 2, and that's selection design using like existing models, using existing parts. So first of all, like why do we do this, right? Why do we care? Why is it important? And so that's what this first slide is telling us. Basically, in short, there's no need to reinvent the wheel, right? That's a saying. The idea is someone else probably already made a model for what you want. And so there's really no reason for you to make a model for yourself, unless you want to practice your skills. But in terms of like getting your project done quickly, sure, go ahead. Take a model that someone else already made and put it into yours. And not only does it let you save time, but a lot of times you can get parts from parts catalog where they have standard sized holes or screws or fasteners. And this just allows like parts from different places to come together, fit together, and work nicely together. And it just creates a lot of standards, right? So every place is the same, and you don't have to like develop your own unique parts that only work with your robot. You can actually use parts that you can swap out and replace easily. And so a couple examples of the catalogs. McMaster is one that I think Eugene showed you last time in CAD Level 2. So I won't spend too much time. It's a little bit of a review. But McMaster is a general hardware catalog where it has a lot of different hardware parts like these screws, eye bolts, washers, nails, and all sorts of things. So you can like, let's say we want to get a screw, you can click on this, you can select which one that you want, just go with the rounded head. There's even more options. And let me just find one. And at this point, you can like click on one of the product informations in product detail, and you can download a file. This is the step file, or there's other formats, but this is a file that you can import into Onshape. So it downloads a file to my computer, and on Onshape, I can, let me, if I remember this correctly, import, let me get the step file, import the document. There's some options I can choose if either there's like, it's a model with multiple parts, or if I want to change what direction up is. And then it just imports this, and I think once it's done, you can see it shows up here. And this is just like a part studio. And you can see it's really small, but there's my screw, right? That's the screw from McMaster. I didn't have to CAD this at all. Someone else did this for me. And I know for a fact it's like the standard size. If my models work with this screw, it's going to work with a lot of other screws. And it just makes my life a lot easier. Instead of like imagining like trying to CAD these threads, that would take a long time. And even CADing this head with the bolt, that would take a lot of time, which you don't need to spend, right? Someone else already did it. So you don't need to spend the time to do it yourself. But sometimes McMaster isn't really what you want. You want a more specialized catalog. So a good one that we found for robotics specifically is this Rev Robotics site, which has a pretty vast catalog of parts that specifically are really useful when you're creating robots. So it has a lot of like wheels and gears and sensors and all sorts of things that are just really useful when you're building a robot. And so like McMaster, you can go to the site and you can search up parts, and they'll have files for you to download that you can import into your CAD. So the next section is just talking about like, what are these things that you want to import from the catalog? Like, what are these interesting parts and what are they used for? So the first big category are fasteners. And fasteners, they fasten things together, which means they like connect things, they attach things. And so you are probably very familiar with a lot of these already, like screws and bolts and nuts. So there's a bit of difference like in technicalities of what is a screw, what is a bolt. Typically, the difference between a screw and a bolt is screws are sharp at the end, and they're meant to like dig into some sort of material. And the end of the screw is like not going to come out on the other side, right? It's going to get stuck halfway in the middle or something like that. Bolts, on the other hand, are designed to pass all the way through some sort of material and then poke out on the other side. And then you can use a nut, which is this thing right here, to close up a screw onto the other end of the bolt. Okay. Typically, bolts are oftentimes also like thicker, but that's not a big difference. Both of these are used to attach kind of two pieces together or multiple. There's also a really interesting type of nut right here. This is called a nylock nut, and it's kind of hard to see in the picture. Let's see if I can, maybe I can make the picture bigger for a second. So what's interesting about this nut is it has a piece of like nylon, I think, or just a kind of a piece of rubber at the end of the nut. And what this prevents is sometimes when you have a part that's moving around a lot, there's vibrations, and those vibrations can over time unscrew your nut. And what this piece of rubber does is it kind of reduces that impact and makes sure it doesn't loosen over time. Because that's actually a big problem with these parts. You might not have had much experience with it, but when you're building some sort of like mechanical object that's moving around, that's shaking about, things are going to get loosened. Things are going to loosen over time, and so this is one way to prevent that. Another way, super simple way, is you can actually like super glue your nuts shut. That's one thing people do to make sure they don't unscrew. Finally, there's washers that kind of fit into this category of fasteners, but they're also kind of serve a different purpose. You're probably most familiar with these flat washers, which are kind of just like discs of metal. And they're typically used to either act as spacers to make sure things aren't touching each other, just to add a little bit of space between two pieces, or it's used to distribute a force. So like if you have a screw, for example, and you want to make sure it doesn't leave a mark on like a piece of wood, you can add a washer and it spreads out the force of the screw so that instead of like having a lot of pressure in one point that might damage the surface, you kind of spread it out a little bit and make it a little bit more even. There's also interesting like split washers, which is over here. Essentially, it's a washer that's been cut and kind of like ripped slightly apart. And the purpose of this is that this washer kind of acts as a one-way nut at that point. It can tighten, but it won't loosen. You can tighten it very easily, but then when you try to loosen it, it kind of bites into the screw or the bolt, and it doesn't let you unscrew it. And this is another kind of useful trick, just like these nylock nuts, that prevent it from loosening easily. With all these fasteners, there's standards for the threads. So you want to make sure like your nut works with your bolt, right? You want to make sure the threads work with each other, because sometimes you might buy a nut that has a different type of threading than your bolt and then it just doesn't screw on, right? So I think Eugene also mentioned this briefly, so I won't spend too much time, but there's essentially something called a tap chart, which tells you all the different standards. And in short, there's two things that determine your threads. It's the diameter of your screw or bolt and your thread pitch, which is kind of the angle that they're at. And those two kind of measurements uniquely define some sort of thread. And there's different, all sorts of different combinations of them that give you different names. And so when you're importing parts, you can consult this chart to make sure that they work together. Or Onshape, if you've used the tool wizard before, it actually gives you a lot of this power. It gives you a lot of standards that you can use. Next category of like useful things that you might want to have are bearings. So I'm not sure if it's probably not popular anymore, but a couple years ago, like fidget spinners were really, really popular, I know. And so fidget spinners
Yeah,
were
I
kind of
remember fidget spinners.
yeah. So fidget spinners, essentially what they were is they're just a bearing with pieces of plastic. And a bearing, all it is just allows rotational movement. And it does it in a way that reduces a lot of friction. So it spins really smoothly and for a long time without wasting energy to friction. Because friction is kind of, it generates heat, it wastes energy. Friction is bad. So bearings just allow rotational movement in a manner that has a lot less friction. So it goes a lot more smoothly. And this is called like a ball bearing. And so if you look at it, it kind of looks like there's little metal balls between the two rings. And that's what allows it to rotate really smoothly and without much friction. So kind of the more useful thing that we'll talk about, one of the more useful things that you're going to use for an upcoming project, when we're talking about wheels, right? We're kind of designing a robot right now. Obviously, you would want you got muted. Okay. Just checking, can people hear me now?
Yeah, I can hear you.
Okay, nice. So wheels, you want your robot to move around, right? You don't want it to be a stationary block that just sits there. Probably want it to move around, navigate, steer. And so you need wheels. And so before we talk about robots, I have a kind of a question for you. So I'm sure all of you have ridden in a car before. Can anyone tell me, how does a car turn or steer? Right. Just very basically. Like you have a steering wheel that you turn, but how does that tell the wheels to turn the car or move the car?
Isn't it like, I think it's the gears. Like when you pull it, it will like push or like pull the wheel.
Yeah, so they're kind of, the steering wheel is kind of connected to the wheels. And what I was trying to get at is in a car, or most cars at least, the wheels themselves turn, right? So if you're turning the steering wheel to the left, most likely your wheels are going to turn as well, right? They're going to rotate like that. However, our robots, when we're designing them, we kind of don't want that behavior. We want stationary wheels because they're just easier to attach, but we still want some way of steering our robot, right? Um, and so one way you can do this is with some really interesting wheels. And so there's two types of wheels that allow you to do this, basically steering without actually turning them. One of them is called mecanum wheels. Um, Not exactly sure about the pronunciation, but an example, what it looks like is right here. And so it kind of looks like a wheel, but if you notice, instead of just like a rounded outside, it's actually composed of these like rollers that are kind of angled, and it's kind of like a spiral or a helix around the outside of the wheel. Right? So a car wheel looks something like this. It's just plain, flat, round, all the way around. These special wheels are made of these rollers that are placed around the diameter, the outside. And what this allows you to do is actually to move your robot in pretty much any direction that you want without turning the wheels themselves. And so I have this kind of chart right here. It's not, you don't have to memorize it or anything, but it kind of gives you 6 different movements that you can do in your car, in your robot, just based on, do you turn a wheel forward or backwards? What do you do with the front wheels? What do you do with the back wheels? And so if we just look at an example of this, I mean, the most simplest movement is just like going forwards or backwards. That is just like any other wheels. You just power all of them forward to go forward, power all of them backwards to go backwards. But what's really interesting is with these wheels, you can actually go sideways, right? Without turning, you can just move sideways. And the way you do that is you kind of have your wheels going in opposite directions. So your top left wheel is going forward, your top right wheel is going backwards, and it's reversed on your back wheels. So your back left wheel is going backwards and your back right wheel is going forwards. Okay, the blue arrows tell you which way they're turning. And then in this fashion, your car is going to move straight to the right. Right? This is something a normal car wouldn't be able to do, right? Like a normal car, you can't just like slide it to the right or power it like that. But that's like why these special wheels are interesting. They allow more unique movement for your car. Similarly, you can just power these diagonal wheels and your car will go up and to the right diagonally. Right? A car can't do that. It can only go straight forward, straight backwards, or kind of turn like that. Right? Another kind of similar thing to this, you might have heard something called omni wheels. And omni wheels are kind of like this. The exact pattern that you drive them might be a little bit different, but they also allow basically free movement across the plane. So you can go forwards, backwards, side, left, turn, um, rotate, diagonal, all sorts of different directions. And so they're pretty cool in that way. Then the other thing that's more relevant to the robot itself, um, you have to have structural members. So the robot, like, it needs a frame that everything sits on, right? Like it needs what's called a chassis, kind of just a base where the wheels are attached, maybe your arm is attached, maybe you have other components that are attached to it. And so what makes up the chassis? It's going to be typically these like structural members. And so they're not really flashy. They're just kind of like bits of metal or um, typically metal. And some 3 common structural members are like tubes. And so that's what's pictured right here. It's not like a tube that you might think of normally. Normally we think of tubes as rounded, but these tubes don't have to be circular. This is like a square tube almost. And these you can kind of cut up in different shapes and you can weld them together, which is just a way to attach them. Like it's kind of like gluing them together, but welding is you're kind of like melting metal and fusing it together. You also have 80/20 beams, which are very popular and really easy to work with. Their shape is kind of standardized, and they have basically these beams with kind of these ridges that you can slide connectors to, and you can just kind of attach them together with the brackets. It's kind of like a Lego set almost, or yeah, it's kind of like Legos. Like they're designed to specifically to work very well with each other, uh, and you can use them to build pretty much any shape. They're very flexible. And in a similar way, there's something called C/U channels because they look kind of like a C or a U, and they're similar to the 80/20 beams. They're just like pieces of metal that are you can put together in a lot of different ways. You can cut it up. You can have brackets that connect them. And this is part of the Rev catalog that we mentioned in a previous slide. And so you can find this file and you can put it onto Onshape. 80/20 beams you can find on McMaster. So if you go to McMaster, you can search 80/20, and it's all of these are different 80/20 beams. And so like here's one of them where you can find the part and put it into Onshape if you want to use it yourself. So that's actually most of the content for today. So going to the CADing, kind of practicing this, wrapping things up. The first thing we have is finishing up the robot arm, which was our first project for this class. And so you've already been working on this for 2 weeks already. You've built the base and hopefully the arm. And so we're going to try to finish it up this week. Okay. And so this is a reminder, the purpose of this arm is to pick up this thing called a wobble goal. Right? So that's the whole purpose of the arm, to grab this and lift it up. Today, we're going to work on the hand, which is the last part of this robot. And that's kind of what's attached at the end of the arm. It's kind of what's used to grab the wobble goal. We have some constraints, which are right here. Mostly it's you have to fit in a specific size. And this is like when it's all closed up. So maybe it can open up to larger than this size, but when it's closed up, it has to fit inside this box. This is just simulating like when you're building a robot, you can't just make a robot that's any size that you want. You have to make sure it's small enough that maybe there's requirements, or just to limit the weight. There's a lot of reasons why you might want to reduce the size of something. And then of course, the purpose of this arm is to grab the wobble goal. So the hand must have some way to grab the wobble goal, and it must also have a way to mount to the arm that you already have. Right? And so just as a kind of refresher, this is the example arm that we've been looking at so far. But I actually want to take a moment and kind of ask you guys, if we look at this arm and think back to the goal that we have, which is to lift up this thing, I would argue that this hand is actually not the best design, right? So like, if you imagine how this hand works, it kind of like pinches up, but the shape of it only allows it to like close so that like these two corners are touching. So you're not going to try to like pinch this center part, right? You can't pinch it together with these like sharp corners. It's probably not going to hold very well. It could still work though, because you could close it up and form this ring, and you can kind of put this over the goal and use it like, let me demonstrate, like if this is the goal, you could close it up and like just based on gravity, it kind of pushes against the ring and it stays in place that way. And so you can use it to lift it up by turning it. But I would challenge you to design kind of see if you can come up with a better shape or design for the arm, rather than just copying this one. The design of this was pretty arbitrary. We just did something quick to have as a demonstration, but I'm sure with a little bit of creativity, you could come up with something that works a little bit better than this. But that's what I want to work on for the first, let's say, the next 20 minutes of class. If you haven't completed the arm, which is like the center bit right here, we can also work on that together. But mostly we want to wrap up this part of the project today so we can move on to building the robot itself. So at this point, if anyone has any questions about how to get started or the homework, the arm, if had troubles with that, I'd be happy to take any questions. If not, I could design a sample arm right here as well. So I'll just start doing that since I don't think we have any questions. Let me make a new part studio. So I'm gonna design a even more basic hand than the one that we have here. I'm just gonna design kind of a ring as the hand. So I can make a sketch on the top plane. I can make a center circle based on the origin. And I want a ring, so I need to make 2 circles, one for the outside and one for the inside. And then I need some way of connecting this to the arm itself. So maybe I can add a rectangle that is like, comes out like that, and that will attach to the arm. At this point, I need to kind of start dimensioning things. So first I have to dimension the circles. So I can dimension this. We want to fit it within a 6x6. So this one maybe should be about 2 inches. This one can be about 3 inches. And then I want to add some constraints. So to position this properly, I can perhaps make a tangent constraint so that that's touching. And then if I look at what's left, let me get select. What is, I need to dimension this because I don't want this to move around. So like if I dimension this, maybe I want it like a 0.5 inches, something like that. Looks about right. I also want to dimension the length of it. So that looks maybe a little bit short, so I'll do 3 inches. And then finally, if we look at what's left, essentially it's free to move around, which we don't really want. And so one way to do that is I can create a midpoint, and I want to make the midpoint horizontal with that point, right? I want the midpoint and the center to be horizontal to each other. So I can add a constraint to move it around. And now you can see everything's kind of black and defined. This is where I want to get at. Once I have my sketch, it should be familiar. Now I just need to extrude. So I can hit my extrude. I'm just gonna extrude my sketch like that. And maybe 1/2 inch, something like that. Looks about right. So that's my hand, quote unquote. It doesn't even open and close, but this probably would work to pick up the wobble goal, because you can imagine you put this over kind of this rod part, this part that sticks up. The ring goes on top of it, and then you start turning the ring and it kind of turns the wobble goal and you pick it up that way. So it doesn't need to be even fancy. It doesn't even need to have any moving parts, right? This is just a solid shape. And so if we bring it here, maybe I can duplicate this assembly. I'll remove the arm from here. And I can insert my new arm right here. So it looks like I forgot one important thing. I forgot a way to connect this arm to the hand itself. I need to put a hole somewhere. And so no worries, I can go modify it really quickly. So first, let me check. I think this is a Parse Studio. Let me check what size the hole is, which is this one right here. So I did this before. So I look at these settings, ANSI tapped 1/4, 20 TPI, so on. This is just a standard. ANSI is just one of the standards that you can see on the tap chart. These are just typical standard thread measurements. And the reason we do this is so that when you CAD it, it's kind of as realistic as possible, so that when you go from the CAD to the physical design, there's less that can go wrong and less that you can overlook. So if I go back to my new hand, how do I put a hole here? Well, I can create a sketch right here. I can create a point, and it's already horizontal with this center because I placed it when there was this dotted line. And then I just need to dimension where it is. So I can dimension it from here. Maybe I want it 1/2 inch away. Pretty arbitrary. And then once I have that hole, I can use the hole wizard. I use the point. I say I want to make a hole there. And then I use my standards. So this is ANSI tapped number 10, but before it's tapped 1/4. So let me go to 1/4, hit check, and now I have the hole there. I can go back to my assembly, insert my arm, and oops, restore. And now I can mate it together with maybe a Revolute mate, so I can turn around. Oops. So let me select kind of the hole right here. And I can, oh, it didn't select it. I can select the hole right here. And then I can select the hole up here. And you can see it snaps into place. Check. It looks a little bit funny, I'll admit, but you can see it moves around. So you can imagine how this works is maybe you kind of drop it down like that, and then you kind of turn it to the side like that. Right? That's how you'd pick up the wobble goal. Right? This is the wobble goal is in front of you. You drop the ring on top of it, so you're surrounding it. And then once you're surrounding it, you kind of turn it like that to pick it up. You turn around and you pick it up using that hand. Okay. Again, this is just one option that you can do. You could do the grabber option, kind of that looks like this. This one, you have to CAD your arms, your fingers, that will go back and forth. And then you also have to find a way to connect it up to your arm. So the way Eugene did it is he had these bars that have a hole to connect to the arm, and then 2 holes to connect to each finger, right? Each of these could be driven with a servo, which is what he has right here. And that would allow it to open and close like that. So again, these are 2 options. A third option that I can think of off the top of my head is you don't really need 2 fingers, right? You could have a solid piece and then just 1 finger that kind of closes in. There's no real reason to have 2. And so maybe you decide that it's just more simpler, less error if you only have 1 of these, and then the other is replaced by just a straight piece of metal. Yeah. So at this point, I do want to kind of let you guys design your own arms. I think the best practice would be to try to see if you can come up with your own design rather than just copying the example. But if you're stuck and don't have any ideas, that's also fine to look at. The only constraints, if I go back to that slide, really the only constraints is you have to make sure that it's within the right boundary. We were pretty generous, 6 by 6 by 6 inches. So as long as it fits into a box that size, it's fine. And it has to have some way of picking up the goal. So now is where I'm fine to let everyone work and design, but also I'm happy to answer any questions that people might still have. I know I went over the CAD example very quickly because it was just a proof of concept. It's just a very quick design I came up with off the top of my head, but you could design something similar or completely different. Maybe to make it easier, instead of having a full ring, you cut out a little bit so you can have a C shape instead. Or maybe you turn one of these into something that a servo could open and close. So instead of just a solid ring, it would actually open and close, kind of like the fingers. I can also have maybe in a couple of minutes, I can have some volunteers share what they have so far or what ideas they come up with. Peyton, do you have a question or do you want to share?
I have a question.
Sure.
I just created like the two closing ones, but it won't move. So do I just
Kind
put
of like this
Revolut
one?
mates? Yeah, do I just put Revolut mates for that?
Yeah, so you can put Revolut. These
Okay.
fingers are connected right here. And so if I look at the list of mates, yeah, this is a Revolut mate that was added. So let me open that up. You can see it's kind of connected to the top in the finger. I will mention if you go a route like this, kind of a trick that you can do is you can see right now they move independently, right? They kind of are just move one by one. To make them move together, you can use one of the tools in this bar. Technically, it's not meant for this purpose, but you can do it. You can add a gear relation. So this gear relation takes two Revolut mates. So this one for the left finger and I think this one for the right finger. It takes two of them and makes them go together. So now when I move one, it moves the other. But notice it's a little bit off right now. You don't want it to move like this. You want the reverse direction where turning this one, if we look at it like this, if I turn this one clockwise, I want the other finger to go counterclockwise, right? So they're reversed, right? if I don't have this, when I turn this one clockwise, this one also goes clockwise, which if we look at here, so like if I turn this one clockwise, it turns the other one also clockwise, which is not what we want, or most likely not what we want. But that's something you can add after you do the revolute mates. So now you can see it, they both move together. It's a little bit slow. Oh, yeah, it's a little bit choppy. But you can see they grab that. Again, you might want to change the shape of this. So like here, what Eugene did is it was just like a simple square shape or corner shape. But if you notice, it doesn't like close all the way. If you were to build this in real life, it would close up to about here and then it would get stuck, right? Because then the two fingers are hitting each other and they can't close anymore. So maybe you want to design it so like you cut off a little bit of this corner so it can close like completely, right? Maybe you want to close in this position. And so you'd want to remove some of the finger, want to cut it away. Another option, if you want to go fancy, you could probably design a hand that has 4 grabbers. So not just like these side ones, but you could add ones that come out like from here and here. That would require a lot more CADing, probably. You could just reuse the model for each of the fingers, but you would have to redesign this attachment point. But I think that would look pretty cool. Although you might want to consider, does that really help you with picking up the goal? Because on one hand, it's nice to look cool, but on the other hand, the most important thing is, does it work, right? If it doesn't work, it doesn't matter how cool it looks. Yeah. Yep. So we'll stay on this until about 6:50, at which I will introduce the last thing for today. Let's see. How would I design this? So it has 4. Yeah, maybe I can try to do that really quickly. It would be, I could do it in a way that it would not be realistic, most likely. Oops, store. So let me fasten. Let's see, can I fasten this to here? But then I'd want to move it down a little bit. Not that direction. So I can move it like that. I can attach this one to here. Oh, looks like it's positive. So this is not exactly realistic because you can see they're intersecting at this point. So you might want to redesign it so that it's just one piece and you get rid of the intersection. But this is just a demonstration. I need 2 more fingers that I've CADed. And I can revolute them just like the other ones. So that's a little bit. think that's a little bit off. I think I did that wrong. So I want actually this hole to be connected to this hole. Like that. And then I want, if I imagine this, I want this hole to be connected to this hole. So, oops, I think flip it around like that. Let me pull it out. So now I have like 4 fingers, and if I change my gear relation so that includes, oh, it looks like the gear relation only works with 2. But you can see these ones are now connected. And then I can add more gear relations to redo. Oops, I think that was the wrong gear relation, but that's all right. Okay. So does anyone want to share any design that you came up with? Okay, Peyton?
So my claws, they won't work, but I'll just show it.
Okay.
Mine's kind of odd looking, so like it's not really like cool, but like I don't know
Oh,
if it'll work or not.
that definitely looks nice. Okay, so
Like, oh, whoops. Like I can animate it, but like when I animate, it goes really weird. Like uh, it goes like 360.
yeah, so what you have does look pretty nice. I like the design that you came up with. Um, what you can do is you can, I think what you were doing, you can limit the movement. So you could do like plus or minus 60 degrees. So like start at
Mm-hmm.
negative 60 and at positive 60, and that would kind of go back and forth. Yeah, or
Okay, thank you.
plus or minus 90. Yep. Um, does anyone else would want to share their design to the class? Um, that's all right. So if I take my share back and go back to the slides. Um, so hopefully either by the end of today's class or during the week for homework, you can finish up the robot arm. The next step is we want to move away from the robot arm and start building the robot. And so here is the first step of doing that. It's building the chassis, which I kind of touched upon before. Here's a picture of an example that we did with the same example robot arm. And now we've built like a chassis, a frame for which to attach to, right? And so this is simulating kind of the body of your robot. This is where everything else is going to connect to. We're going to add wheels for it to move around, maybe some sensors. It's kind of up to you, but you need to make this frame. And so to do this, you can, it's fine if you want to just create some of these beams yourself. So like you could just create a rectangle and extrude it out. That's perfectly fine. And you can create a couple of these of different dimensions, and then you can fasten them together. Or if you want a challenge, you can find 80-20 beams or other structural members that we talked about in the previous slide. So if we go back there really quickly, we have tubes, 80-20 beams, CU channels. These are all examples of structural members. So you can find some of these on the parts catalog that we talked about before. McMaster has these 80-20 beams very conveniently. And you can work with them to put it together instead of using your own extruded ones, just for practice. And so I have the file here. So look here, kind of here's our imported parts. Like here's one of the beams. Here's one of the brackets that are used to connect the beams together. And I think this is a longer beam than this one. This is a shorter one. And so in the assembly, we just imported a couple of these beams in. Just insert, I can insert like this in if I wanted. This is one of the long beams. Right? And then I can use my fasten mates to kind of connect them together. Or the way this one was done, we actually used plane mates. So it's actually pretty annoying to work with the 80-20 beams. That's why it's a little bit of an added challenge. So there's no easy like fast like mate connectors to connect these up together to select. And so the way we actually did this one is we used planar mates. So we made sure that the top of this beam and the top of this beam are all on the same plane. The side of this beam and the end of this beam are all on the same plane. And then the bottom of this beam and the bottom of this beam are on the same plane. Something like that. Once you have 3 planar mates, it kind of restricts the movement, fully defines it. And you can see at this point, if I unfix this, if I move one part, it moves the whole thing. Like everything is fixed together in that way. And so you want something that ends up like this. You want to build some sort of frame. You can import your robot arm. The way you do that is you want to go to insert. You can go to other documents and I can find my document, this robot arm. It might ask you to say create a version or go to assemblies. It says create a version. You have to first create a version and then you can kind of just like click this one and
Wait, I have a
drag it in.
question.
Yep.
Can you like send us, the link to this document
Yes.
in case we can't like make it?
Yeah, so we will post this on Google Classroom for you to look at on how to do this. I'd say the easier way to do this, if you're not as comfortable doing this, what you can do is, let me create a new part studio. Instead of using the 80-20 beams, you can create your own. It will make it a little bit easier. So you can make a sketch. I'm just gonna create a simple, like maybe like a 2x2. Dimension this to do 2 inches. Dimension this to be 2 inches. And maybe I don't want to revolve. I want to extrude this out. I'll create my own beam. I can make it like 10 inches or something. It's a little bit short, maybe 20 inches. So I can use this instead, and I can create a new assembly. I can insert my CADed beams like this. So maybe I want to make a square. So I create 4 of these, right? These are gonna form my frame. It looks like they're not exactly square, but that's okay. So there's a couple ways that you can connect these up to each other. So probably the easiest way is to do fasten mates. So you can use a fasten mate, and I say the end of this, or like the top right here, top edge, is gonna connect to this top edge. And maybe that's not exactly what I was going for. I can use these arrows to bring it. That's what I was thinking about at first. I can hit check. I can drag these out a little bit to make room. I can say, again, like kind of looking straight on, this bottom edge is going to connect to this bottom edge. And again, it's not exactly in the right position at first. I can rotate it around. And now it's like, I want it to be on the inside, not the outside. So I use this to rotate it around. and now it's in the right position. And then I just have one more beam, so I can, once again, say like the top of this edge connects to the top of this edge. And oh, looks like that's not gonna work correctly. That's not gonna fit because I need it to connect like this, not like that, right? I need to connect it like that. So instead, what I'm gonna do is I'm gonna fasten this edge with this edge. I'm gonna do that. That looks about right to me. Hit check, and now I have kind of a very simple frame. You might want to add another beam in the middle so that you can, or maybe it'd be easier in the middle here, so that you can add the arm. So I can actually do that right now. I can add another, or not a 80-20. I want to do this. Get rid of this beam. And so now I can like fasten this one, the center of this, to the center of here. It's on the wrong side, but no worries, I can use these arrows to kind of flip it around, just like that. I can rotate it around if I'd like. And now I have like kind of a center platform to put my arm. I can insert my robot arm. Assemblies, I can put my new one here. And now I just do another fasten meet. I can like fasten this robot arm to here. Solve it. And there we go. So now you have kind of a simple chassis. It looks a little bit odd because it looks like my arms, this isn't the right position for it because it's kind of too short, right? Like the frame is a little bit too big compared to the arm. So the arm right now is not able to reach far enough, right? So that's why we had the constraints of kind of how far you have to reach or whatever. Also looks like I didn't put it exactly in the right position because it's kind of intersecting at this point. But anyways, that's about it. Again, to summarize, you can create your own beams like this just by extruding some rectangles, right? I just created a rectangle, I extruded it out a little bit, and then I use that in my assembly like this. Or you can import these 80-20 beams or similar structural members from McMaster or Rev and use them in your assembly instead. It will be slightly more complicated because if I go to like my fasten meet, for example, it's gonna start like complaining. There's all these different points that you can attach to. And that's just because in the real 80-20 beam, it's a lot more complex than just a square or a rectangle. And so you have to be more careful about where you're attaching what to. Right? But overall, it's the same process. You kind of just match up what points connect to each other and you just rotate it around if necessary. And you form some sort of frame. Okay. That is about the homework for next week. So the constraints is pretty simple. All that you need is some place that you can attach your robot arm base to, as well as enough space to attach wheels and other components later on. So that will be homework, as well as if you haven't finished up your robot arm, you can do that. I will provide the example on Google Classroom for you to take a look at. But that's about it. It's 7 o'clock. So if you have any questions about the ARM or the CAD things or lecture material that we talked about, I'll be sticking around to answer any questions. Otherwise, have a good week. And I believe I will still be teaching next week. And then after that, it'll be Eugene for a couple of weeks.